Hello students. Now let's move on to next topic. Integral as a limit of sum. Integral means Riemann Stieltje integral expressed as a limit of sum. Okay, it simply means that. And you will come to know this clearly in the upcoming stages. Okay, so similar to Riemann sum, we now introduce a sum which will yield a sufficient condition for the existence of Riemann Stieltje integral. And also you have a theorem based on this. Now coming to the definition part, let P be a partition of closed interval AB and Ti belong to xi minus 1 comma xi. So this is the subinterval of this closed interval AB. Then the sum S of P comma F comma alpha is given by the formula S of P comma F comma alpha, which is equal to summation I equal to 1 to n F of Ti into delta alpha I. Okay, and see here there is a small thing you need to note down. U of P comma F comma alpha and L of P comma F comma alpha is unique for respective partition, but this is not the same with the sum S of P comma F comma alpha. See, this has many values depending on this Ti. See here, S of P comma F comma alpha is summation I equal to 1 to n F of Ti into delta alpha I. If I expand the summation, it is F of T1 delta alpha 1 plus F of T2 delta alpha 2 plus etc. up to F of Ti delta alpha I plus etc. up to F of Tn delta alpha n. Okay, delta alpha n. And this Ti is picked from the subinterval xi minus 1 comma xi. And this T1 is picked from the subinterval x0 comma x1. And similarly, this is picked from the subinterval x1 comma x2. And similarly, this Tn is picked from the subinterval xn minus 1 comma xn. So here there are actually many points, infinite points in this subinterval. There are infinite points in this subinterval x0 comma x1. But here we are picking T1. We are picking only one point, and f of T1 into delta alpha 1. Delta alpha 1 means alpha of x1 minus alpha of x0. Okay, and plus f of T2. T2 here means it belongs to this subinterval x1 comma x2, and this is any point. This is an arbitrary point in this subinterval x1 comma x2. And here Ti is any point in this subinterval xi minus 1 comma xi. Similarly, Tn is any point from this subinterval xn minus 1 comma xn. So this is for one set of T1, T2, Ti, etc. Tn values. But you can choose many such set, okay, which is completely different from this T1, T2, Ti, Tn. Okay, so you can construct many such set consisting these type of points. So these points must satisfy the condition. That condition is that it should belong to this subinterval, particular subinterval. Okay, and there are many points, as I told you earlier, there are many such points in this subinterval, and obviously you will have many such sets containing T1, T2, etc. Ti, etc. to Tn. So for that respective set, you have particular S of P comma F comma alpha value. Okay, and note, Let mi and capital Mi be the infimum and supremum of f in ith subinterval, that is xi minus 1 comma xi, and ti be any arbitrary point in xi minus 1 comma xi. Okay, as I told you earlier. Then mi is less than or equal to f of ti less than or equal to mi. So here actually, see, if this is domain and this is codomain and this is the function f, okay, and here you have many points, okay, and the points of this domain will map to some points in codomain, and I will call this as range, and in this range you will all have the images of these points. Okay, you will have the images of these points which are in the domain. So that is actually called as range. See here, and here you have the subinterval. Like here you have xi minus 1 comma xi. Okay, in this particular subinterval, you will have some images here. Okay, and I will take that as some set here. Okay, and here in this set there are images of this subinterval. Okay, and here in this set there exists infimum as well as supremum, and in that small mi is taken as infimum, capital Mi is taken as supremum. Okay, so and that f of ti, that is f of this, okay, if ti belongs to this interval, then obviously f of ti belongs to this set. And also if I take mi and capital Mi as infimum and supremum, obviously the ti which belongs here to this subinterval, corresponding that f of ti will be mapped here, and that will lie between the infimum and supremum of this particular subinterval. Okay, so that they are telling. So here mi less than or equal to f of ti less than or equal to capital Mi, and if you multiply delta alpha I throughout and summing up from I equal to 1 to n, we have summation I equal to 1 to n mi delta alpha I less than or equal to summation I equal to 1 to n f of ti into delta alpha I less than or equal to summation I equal to 1 to n mi into delta alpha I. But this, according to the definition of lower sum, it is equal to L of p comma f comma alpha, and this is nothing but S of p comma f comma alpha, and this is nothing but U of p comma f comma alpha. So you have this relation, okay, L of p comma f comma alpha less than or equal to S of p comma f comma alpha less than or equal to U of p comma f comma alpha. Okay, now let's talk about its convergence. Okay, convergence of S of p comma f comma alpha. See, we say that this sum S of p comma f comma alpha converges to A as norm p tends to 0. Norm p tending to 0 means, see, this is actually the maximum length of the subintervals. So, whichever partition you take, you construct a subinterval, and you will make the collection of those subintervals, and in that you are taking the maximum out of it. So, maximum length out of it. So that was denoted by norm p, and here what they are telling, this sum converges to A as norm p tends to 0. Means you will have many points. You will have many points in the partition P. Then only this norm p tends to 0. So when you have increased number of elements in P, then you have increased number of subintervals, and when you have increased number of subintervals, you have that summation of those elements. See, if you have increased number of subintervals, then you have increased number of f of ti's. Okay, see, because this ti, you should take that ti from each and every subinterval. Okay, so if ti increases, obviously f of ti also increases, and when you sum all those things, that is nothing but this. Actually, when you sum all those things, means f of ti into delta alpha I. Okay, summing from I equal to 1 to n. Okay, and if you sum all those and still you are getting a, it is not a infinite part, it is a finite number. Okay, so then we say that this s of p comma f comma alpha converges to a as norm p tends to 0. See, the definition of convergence also includes epsilon and delta. Okay, so that part is explained here. If for any epsilon positive there exists delta positive such that the difference between this and this is less than epsilon, whenever this is less than delta, see, norm p tending to 0 means we have taken that as less than delta. Okay, because we don't have norm p equal to 0, we have norm p tending to 0, so I will just have norm p less than delta. Okay, whenever norm p less than delta means tending to 0, less than delta, for any choice of ti belonging to xi minus 1 comma xi, where a is a non-negative real number. So we denote it by like this. See, limit s of p comma f comma alpha as norm p tending to 0 is a. See, also I have written norm p tending to 0 or as n tends to infinity. See here, when this norm p tends to 0, when the number of elements in this p increases, partition p increases, that is as n tends to infinity. So whenever we talk about convergence, it means n tending to infinity. So n tending to infinity or norm p tending to 0 here in this case. Okay, so this is all about the convergence of s of p comma f comma alpha. And also you have a theorem based on this. Okay, sufficient condition for Riemann integrability. And here in this sufficient condition, we include this limit of sum. Okay, so here if limit s of p comma f comma alpha as norm p tends to 0 exists, then f belongs to R of alpha. See here, if this converges to some point, then f is said to be Riemann integrable. So here we have got another condition to check for Riemann integrability. That is, if we find this is converging to a finite point, then we can see that this f function f is Riemann integrable. And also we need to prove integral a to b f d alpha is equal to limit s of p comma f comma alpha as norm p tends to 0. See, this only they have written as integral as a limit of sum. Okay, so the heading which we started with was integral as a limit of sum. So this is nothing but this. Okay, integral means Riemann Stieltje integral, and this is expressed as limit of sum. What is this actually? S of p comma f comma alpha, it is summation f of ti into delta alpha I, and we need to prove this one. Okay, so now let's get into the proof. Say, given, what is given? If limit s of p comma f comma alpha as norm p tends to 0 is equal to a. So this is given. We need to prove that f belongs to R of alpha. So what we are taking now, let this, actually this is given. Okay, given limit s of p comma f comma alpha as norm p tends to 0 is equal to a. So it is some finite real number. Okay, and by the definition of limits, or by the definition of convergence, for any epsilon positive, there exists delta positive such that difference between this and this is less than epsilon by 2 whenever norm p tending to 0 means norm p less than delta. I have taken that as some number delta. Okay, norm p less than delta. Name this as equation 1. And this one implies, see here, we have taken the difference between this and this is less than epsilon by 2. So if I remove this mod, then I have minus epsilon by 2 less than s of p comma f comma alpha minus a less than epsilon by 2. So if I take this minus a this side, see, first consider this inequality. Okay, s of p comma f comma alpha minus a less than epsilon by 2. So if that is the case, then s of p comma f comma alpha is less than epsilon by 2 plus a. Okay, and if you consider this inequality, then s of p comma f comma alpha is greater than a minus epsilon by 2. Okay, so here we can write this as a minus epsilon by 2 less than s of p comma f comma alpha less than a plus epsilon by 2. Okay, and here you have this. See, we know that L of p comma f comma alpha less than or equal to s of p comma f comma alpha less than or equal to u of p comma f comma alpha. See here, we know that L of p comma f comma alpha less than or equal to s of p comma f comma alpha less than or equal to u of p comma f comma alpha. And also we have a minus epsilon by 2 less than s of p comma f comma alpha less than a plus epsilon by 2. So we have this. Okay, and here see, just for instance, you consider this as some small a and this as b and this as c. Okay, and here if I take that as a less than or equal to b less than or equal to c, this name this as 1 and name this as 2. So 1 implies this if I take this as a and this as b and this as c. Okay, and also 2 implies a minus epsilon by 2 less than b less than a plus epsilon by 2. Okay, see, if I have this and from these two I can write since b is less than a plus epsilon by 2 and a is less than b, I can write, see here, we have a less than or equal to b and b is less than a plus epsilon by 2. So I can write a less than a plus epsilon by 2. And here, see here, we have a minus epsilon by 2 less than b and b is less than or equal to c. So I can write that implies a minus epsilon by 2 less than c or c is greater than a minus epsilon by 2. Okay, so I have a is less than a plus epsilon by 2 and c is greater than a minus epsilon by 2. So combining these two, we have c minus a less than this minus this, that is a plus epsilon by 2 minus a minus epsilon by 2. Okay, if you expand this, no, it will be equal to epsilon. So c minus a is less than epsilon. And see here, whichever number you take, this holds. See here, whichever number you take means it should satisfy these two conditions. Okay, whichever a value you take, whichever b value you take, whichever c value you take, or whichever epsilon or a. So that should satisfy these two conditions first. If you have chosen in such a way that these two conditions are satisfied, then obviously c minus a is less than epsilon. Okay, so here c minus a is less than epsilon means what is c actually? C is u of p comma f comma alpha, and what is a? L of p comma f comma alpha. That is C minus A means U of P comma F comma alpha minus L of P comma F comma alpha is less than epsilon. See, it means U of P comma F comma alpha minus L of P comma F comma alpha is less than epsilon. So here, so that is how we got U of P comma F comma alpha minus L of P comma F comma alpha less than epsilon here. Okay, it means by the condition of integrability, we have this function is Riemann Stieltje integrable. Okay, so this is how we have this proof. See, and this is the second part of the theorem. To prove integral a to b f d alpha is equal to limit norm p tends to 0 s of p comma f comma alpha. See, to prove this result, in this first part of the theorem, we have proved this f is Riemann Stieltje integrable. So, if f is Riemann Stieltje integrable, then it must satisfy this inequality. See here, L of p comma f comma alpha less than or equal to integral a to b f d alpha less than or equal to u of p comma f comma alpha. Why this is? See here, we know that if f is Riemann Stieltje integrable, then this is equal to its upper integral as well as lower integral. And we know that this is less than or equal to lower integral and this is greater than or equal to upper integral. We have L of p comma f comma alpha less than or equal to integral a to b f d alpha less than or equal to u of p comma f comma alpha. Also, we know that L of p comma f comma alpha less than or equal to s of p comma f comma alpha less than or equal to u of p comma f comma alpha. So, we know that this is lying between these two and also this sum is lying between these two. See, if that is the case, then we have this mod of s of p comma f comma alpha minus integral a to b f d alpha less than or equal to u of p comma f comma alpha minus L of p comma f comma alpha. See here, why is this? Because we have L of p comma f comma alpha less than or equal to integral a to b f d alpha less than or equal to u of p comma f comma alpha. Also, we have L of p comma f comma alpha less than or equal to s of p comma f comma alpha less than or equal to u of p comma f comma alpha. Okay, so here, see here, we have this inequality as well as this inequality. It means this lie between L of p comma f comma alpha and u of p comma f comma alpha, and also this lies between this and this, and we don't know whether L of p comma f comma alpha less than or equal to integral a to b f d alpha less than or equal to s of p comma f comma alpha less than or equal to u of p comma f comma alpha. We don't know whether this is right or this is right. That is L of p comma f comma alpha less than or equal to s of p comma f comma alpha less than or equal to integral a to b f d alpha less than or equal to u of p comma f comma alpha. See here, we just know that these two are lying between these two, and we don't know whether this is less than or equal to s or s is less than or equal to this integral. So we don't know this. So what I have written, see, suppose if this is the case, then we write this s minus this integral is less than or equal to u of p comma f comma alpha minus L of p comma f comma alpha. Suppose if this is the case, then we write this integral f d alpha minus s of p f comma alpha integral f d alpha minus s of p comma f comma alpha less than or equal to u of p comma f comma alpha minus L of p comma f comma alpha. So either we write this minus this less than or equal to this, or this minus this less than or equal to u minus L. So we don't know what comes first. So we have written mod of s of p comma f comma alpha minus integral a to b f d alpha less than or equal to u of p comma f comma alpha minus L of p comma f comma alpha. Okay, so therefore from inequality to, okay, see here we have this inequality to is this difference less than epsilon. Okay, so we have if this difference is less than epsilon, then obviously this also See, if this is less than epsilon, then this also is less than epsilon. So we have this is less than epsilon. So for any epsilon positive, there exists delta positive such that this is less than epsilon. Whenever norm p less than delta, then it simply means this limit as norm p tending to 0 s of p comma f comma alpha is equal to integral a to b f d alpha. See, actually this is the definition of convergence, and that is in place of a we have got this integral. Okay, so in place of a we have got this integral means limit s of p comma f comma alpha as norm p tending to 0 equal to a. Instead of a we have got this, so integral a to b f d alpha. And you need to note down one point, that is above theorem is only the sufficient condition for integrability, but it is not a necessary condition. It's only a sufficient condition. Means if this sum exists, see, if it just means if this limit of s of p comma f comma alpha this exists, then f belongs to R of alpha, but not the other way. That is, if f belongs to R of alpha, we don't have this. It may or may not exist. Okay, so that is what this note implies. Okay, so this is all about the integral as a limit of sum and the sufficient condition for Riemann integrability. Okay, thank you.